All right. Well, what I'd like to do today and on Monday is to talk about NMR spectroscopy and kind of how NMR spectroscopy works. I'll call it concepts and theory. And for me, what I want to do is give my perspective on NMR, which is not a highly mathematical perspective. In fact, everything I write up here today is going to really be, in terms of numbers, is actually going to be simple arithmetic, and most of it is more an embodiment of the idea rather than a specific calculation that you, quote, need to do. So where NMR begins is with the concept that a nucleus of certain sorts, and I'll just write a proton for now, has a spin to it and when you have a spinning charge, it generates a magnetic dipole. And if you apply a magnetic field, we'll call that magnetic field B0, then you have two different spin states or more, and we'll see examples of this in the case of nuclear quadrupoles, but let's start with the case of a proton or a C13. You have two spin states that can exist, quantized spin states. The spin of the nucleus can either be spin up, so if it's spin up, in other words, in the same direction as the applied magnetic field, then this is going to be lower in energy. So I'll put by up, I mean aligned with B0. And if it's spin down, meaning aligned against B0, then we're higher in energy. And we'll refer to, throughout our discussion, we'll refer to the lower energy state as the alpha state and to the higher energy state as the beta state. Now, different types of nuclei have different spin properties. Rather than trying to start with generalizations about rules, I'll come to those in a moment because at some point you'll be wondering in your project, well, could I study chlorine 35 or something like that? Let's just start with typical nuclei studied. So if you go, for example, to the 400 megahertz NMR spectrometer in my building, in Natural Sciences 1, you'll find that that instrument can study protons. I'm going to write a couple of numbers for these. I'm going to write the atomic number and the mass number. And it can study C13. And it can study F19. And it can study P31. And these are common nuclei that are often studied by NMR. They're easy to study. What do these nuclei have in common? 1/2. They have a 1/2, indeed. And what, forgetting their spin state, what property on the blackboard do they have in common? Odd numbers of protons and neutrons, or more specifically, we can group them that their mass number is odd, specifically that the sum of their protons and neutrons is odd. So nuclei with an odd mass number have a nuclear spin. And the quantum characterization of nuclear spin is what's called a spin number. And we'll call the spin number I. Doesn't really matter what we call it, but they call it I. And so that number is going to be 1/2. And that gives you all the ones up here. But if we want to generalize more, nuclei with an odd mass number will have a spin number of 1/2 or 3/2 or 5/2, etc. So that's the more general idea. The ones with 1/2 are easy because they have what's called a nuclear dipole. If you have 3/2 or 5/2 or 1, as we'll see in just a moment, you have what's called the nuclear quadrupole, and then those tend to be harder. So all the ones here of I equals 1/2 have spin states. So we have the quantum number and then the two spin states they can have. And so the spin states are plus or minus 1/2. So that's all of these, H1, C13, F19, we'll come to nitrogen in just a second, and P31. Now, a nucleus with a spin number of 3/2 can have spin states of plus or minus 1/2 or plus or minus 3/2. And this is what you call a nuclear quadrupole. Most of the time, many of the times, nuclei with nuclear quadrupoles don't behave as if they're NMR active. In our next lecture, we'll get to the concept of relaxation. Relaxation basically is how quickly you flip between the two spin states, or in this case, between the 4 spin states, or 3 in some cases. And often they flip very quickly, which means you can't study them by NMR. Relaxation is affected by properties like symmetry as well, and I'll get to that in a moment with another example. But if I give you an example of a nucleus with a spin state of 3/2, so boron, there are two different isotopes. There's B10 and B11. And B11 has, I think they both do, but B11 has a spin state of 3/2. And if you look at the NMR spectrum of borohydride from this one, what you see in the H1 NMR is you see 4 lines equally spaced and of equal height due to the hydrogens coupling with the nuclear quadrupole. And it's very unusual because normally we think about splitting into a doublet, or if you're thinking a triplet, a 1 to 2 to 1 triplet, or a quartet, a 1 to 3 to 3 to 1 triplet. But what's happening here is the hydrogens see boron, and they see either the boron having a spin state of -3/2, or -1/2, or positive 1/2, or positive 3/2. And so you see the 4 spin states, and that gives rise to 4 lines. All right, so let's look at some other nuclei with an odd mass number. So one very important nucleus in biomolecular NMR is N15. Nitrogen 15 has a spin number of I equals 1. And indeed, N15 is often studied. Most nitrogen is not N15. We talked about this when we talked about mass spectrometry. We said that the natural abundance of N15 is 0.38%. And that's really, really low. Isotopic abundance of C13, spin active, is 1.5%, is 1.1%. And you know that carbon NMR is not very sensitive. You need to have a reasonable sample size, more than you have for proton typically, and sometimes often collect data for much longer. Well, by the time you're down to 0.38%, studying it at natural abundance is pretty hard. And so often you do this with isotopic labeling. Two-dimensional N15-based techniques are a mainstay of protein NMR spectroscopy. And in general, since most proteins are expressed these days, what you do is you simply grow up your E. coli with N15 ammonium chloride, and they absorb that and use it to make up the amino acids. And then you can get a fully N15 labeled protein, which is very useful. N15 is starting to become more important in some natural product structure determination. Alkaloids, as you may have seen, for example, in Neil Garg's talk, have lots of nitrogens in them. And so being able to figure out the positions of those nitrogens can be very important. In the case of something like an alkaloid or a synthetic project, you might not be able to put N15 in. NMR spectrometers are becoming more sensitive, and so it becomes not completely nuts to think about using N15 techniques in your NMR. At the end of the course, I may talk about some two-dimensional techniques with N15 at natural abundance that people are doing, just because I think it's useful, but that won't be until the end of November or December. All right, another nucleus, another common well, not common, another nucleus is oxygen. O17, remember we said, is only low natural abundance. It's only very low, I should say. It's only 0.04%. And oxygen 17 has a spin number of I is equal to 5 halves, so that's the nucleus that can have 6 spin states, -5 halves, -3 halves, -1 half, +1 half, 3 half, 5 halves, etc. And so it has sort of doubly dammed, and so it's not generally studied. All right, so that takes care of our nuclei with odd mass numbers. Now, the next class I'll talk about is if you have an even mass number and an even atomic number. So that's easy. Those are nuclei like C12, O16. And the answer is very simple. Those have a spin number of I equals 0. They have no spin. and those are NMR inactive. Since you don't have different spin states, you can't have quantized transitions between spin states, so there's no way they can be studied by NMR spectroscopy. So the last class then becomes nuclei with an even mass number but not atomic number. So that would include nuclei like deuterium, nuclei like N14. I guess that would be the common ones we'd encounter in organic compounds. These all have a nuclear quadrupole. Remember, a quadrupole is anything that doesn't have a dipole, i.e. just spin up, spin down, i.e. I equals 1/2. So these all have a nuclear quadrupole and a spin number I equals 1, 2, 3, etc. So for example, if you take deuterium, you have a spin number I equals 1. And so you have 3 spin states available to it. And do you know the direct manifestation of this that many of you have seen with your own eyes? Who's run a C13 NMR? Most of you. What solvent did you use? Chloroform, right? The first solvent most of us reach for because it's pretty cheap as solvents go and pretty good at dissolving organic chemicals. It's cheap because it doesn't have that much deuterium in it, right? You only have 1 deuterium for all that weight of chlorine. You need the deuterium to get the deuterium lock for NMR spectroscopy. And what do you always see when you run an NMR spectrum in deuterochloroform? A triplet, and a very interesting sort of triplet. So for CdCl3 in the C13 NMR, you see a 1 to 1 to 1 triplet centered at 77 ppm. It's really jammed together. The separation between the lines is 32 hertz. In other words, the distance between these 2 lines is 32 hertz. The distance between these 2 lines is 32 hertz. If you're running your spectrum on a 500 megahertz spectrometer, that means the carbon NMR is running at 125.7 megahertz. I'll come back to that in a second. Which means 1 ppm is 125 hertz, which means the lines here are separated by about 0.3 of a ppm. And that's on a big, roughly 200 ppm scale. So as James said, those lines are really close together. And the manifestation is it's a 1 to 1 to 1 triplet because to a first order approximation, a third of your deuterons are in spin state -1. A third of your deuterons are in spin state 0. And a third of your deuterons are in a spin state of +1. And we'll see in a moment that there are minuscule, minuscule differences in the population of the spin states, and that that's really, really important. We'll also see in a moment that that number 32 comes back when we see something else. All right, most of the time, so deuterium is kind of special among nuclear quadrupoles in that most of the time nuclear quadrupoles, nuclei with quadrupoles, undergo rapid relaxation. But deuterium is special. Its relaxation is slow. And I'll just say, to put it in simple terms, is effectively like NMR inactive. So many of the nuclei with nuclear quadrupoles, like chlorine 35 and chlorine 37, how do we know that those have, well, all right, I will take that back. We can't know whether they have a nuclear dipole or a nuclear quadrupole, but we know they have a spin number of 1/2 or 3/2 or 5/2 or 7/2. They happen to have the higher ones. So we never see J coupling. We never see spin-spin coupling to chlorine 35 or chlorine 37. If we did, your carbon spectrum here, your C13 NMR spectrum, would actually be much more complicated because you'd be seeing splitting from the chlorines. Okay, so nitrogen 14 also has a nuclear quadrupole. It has a spin number of I equals 1. And so normally you have rapid relaxation. So for example, if we come to that amide, what we were dealing with before when I asked you about the IR spectrum, and if we look at the NMR spectrum of this amide, of course, most of your nitrogen, 99.62% of your nitrogen, virtually all, is N14 in here. And we don't see J coupling to this proton. So as I said, the fact that we do see J coupling between the deuterium, J coupling just means spin-spin coupling to the C13, is because deuterium is the oddball here in that it often doesn't undergo relaxation. But most nuclei with a nuclear quadrupole don't show nuclear coupling because we have rapid relaxation. As I was saying earlier with my example of borohydride, symmetry is the oddball on, or highly symmetric species end up being oddballs in that you have slow relaxation. So borohydride, BH4-, has tetrahedral symmetry, so you see coupling from the boron to the hydrogens. A case that you may see, and I saw first by accident, one of those cases where you simply dissolve up a compound in a solution and you get an NMR spectrum. And so this is ammonium chloride in DMSO, right? Ammonium chloride has NH4+, Cl-, and the ammonium has tetrahedral symmetry. And the first time I happened to accidentally have this in a sample and took an NMR spectrum, as I said, in DMSO D6, I saw an NMR spectrum with 3 peaks that were so far apart that you barely could tell they went together, except the odd thing was they were all the same height. and this spacing was the same as that. And it's like, what's going on? Oh, wait, that's your nitrogen. So this is your J1 NH. In other words, your one bond coupling between the nitrogen and the hydrogen. I don't remember what the coupling constant is, but it's big.
It's always referred to as J, no matter what's.
J is the term that we use to refer to spin-spin coupling.
It's not just proton NMR when we do that, right?
Not just proton NMR. So we would describe this as J1 CD equals 32 hertz. And later on, when we start to talk about 2D techniques like HMQC and HMBC, terms like J1CH, J2CH, and J3CH, in other words, 1 bond, 2 bond, and 3 bond carbon-hydrogen couplings will become very important in structure determination. All right, so when we last left our spinning nuclear dipole, he was spinning in the presence of an applied magnetic field. And I said there were two states, the alpha state and the beta state. And the alpha state was lower in energy than the beta state. So I can make a little diagram, E, and I can show, just like you learn in electronic structure, where you learn, for example, you have pi orbitals and pi star orbitals, and you have populated electrons in your two orbitals. Here we can think about populations of nuclei. It's a little bit different in the sense we're talking over the entire sample. But if we have our applied magnetic field B0, and we have our alpha state and our beta state, remember, the alpha state is aligned with the magnetic field. We can think about some nuclei being in the alpha state and some nuclei being in the beta state. And there's an energy gap between these two spin states. And we can think about the energy to flip a nucleus from the alpha state to the beta state as the energy of a photon, in other words, an energy quantum in the electromagnetic spectrum. And that delta E is going to be h nu. In other words, the energy, the difference, the frequency of a photon to flip a nucleus from the alpha state to the beta state is going to be dictated by that difference in energy, such that E equals h nu, delta E equals h nu. Now, what sort of energies are we talking about? Well, we're talking about 500 megahertz for a proton, so we're talking about radio frequency. So let me just give you a calibration here. So if you think about UV and our delta E, so maybe if I think about UV and I think about a chromophore, maybe I think about my mercury line at 254 nanometers from my TLC lamp, and I think about a chromophore, say, containing a benzene ring or a methoxybenzene ring. And maybe I say, all right, if we just take 254 nanometers, and I go ahead and plug into, remember, C equals lambda nu, so that's our wavelength, and you calculate nu, the frequency, and then you calculate E equals h nu, and you plug in with Planck's constant, you get the delta E corresponding to a photon in the UV is 113 kilocalories per mole. And then you stop and you think like an organic chemist and say, OK, wait, what's 113 kilocalories per mole? What's the difference between a pi and a pi star? It's a little stronger than the strength of a carbon-carbon single bond, a little stronger than the strength of a carbon-hydrogen bond. In other words, the energy difference in the UV spectrum corresponds to the strength of bonds. And now if you think about, so this is our UV. If we think about, oh, I guess I wrote UV. All right, if we think about IR, and I think about a typical stretch, well, we've been talking a lot about carbonyls. Carbonyls absorb at about 1700 wave numbers. We said that wave numbers was centimeters per wave, which meant your wavelength is 1/1700th of a centimeter, and that's lambda, and then you calculate your frequency out, and it's in the infrared range, and then you plug into delta equals h nu, and you find out that delta E is equal to 4.87 kilocalories per mole. And you say, okay, that kind of makes sense. I know that infrared is lower in energy than UV. It's lower in energy than visible. I know that we don't have sufficient energy to break bonds in the IR. Indeed, all you're doing is kicking them up a higher vibrational state. And you remember your energy curves with your vibrational states, and it takes many jumps before you get to the point that you're dissociating bonds. Well, if we do the same for NMR, and let's say we take 500 megahertz, and we plug in, and again plug in E equals h nu, then delta E is equal to 0.0477, but it's not kilocalories per mole, it's calories per mole. So the first thing when you see NMR spectroscopy is you're getting dinged badly because the technique involves very little energy absorbance. In other words, when you're measuring a UV spectrum, it's very easy for a detector to detect the energy of a photon. And when you're measuring an IR spectrum, it's very easy. And already your detectors have to be much more sensitive. And it's going to get worse from there. All right. So we talked about delta E equals h nu. What's new for a, that's not a pun. If it were, it would be terrible. What's new for a nucleus? Nu is dictated by gamma B naught over 2 pi. Okay, well, so far so good. I said B naught is the applied magnetic field. So if you look at this, you say, oh, well, this kind of makes sense. Bigger applied magnetic field means bigger difference in energy, right? Delta E equals h times gamma B naught over 2 pi. So that kind of makes sense. All right, let's just take a look at that. What does that mean? There's a linear proportionality. So if I again plug into this equation, I get that let's see. So in other words, if I just go ahead and plug in to this to this equation, I'll come back to gamma in a second. We find out that if we apply a 70,500 Gauss magnetic field, that leads to 300 megahertz for H1. If we go to a higher magnetic field, that leads to a higher frequency. It's going to be in a linear fashion. So if I apply 117,500 Gauss magnetic field, now we're at a 500 megahertz NMR spectrometer. And if you make a 300 megahertz NMR spectrometer, you have an electromagnet like this, maybe this big, a superconducting magnet this big, where you have a coil of wire with electricity passing through it in liquid helium, and the wire is superconducting, so the electricity flows and flows and flows without any resistance or diminution, and you get a strong magnetic field. In order to build the technology to get a uniform 117,500 Gauss magnetic field, you need a kettle about this big across and about this high to house the superconducting magnet and the liquid helium and the shims and so forth. And finally, if you get to, say, an 800 megahertz, and of course it's all linear proportionality, you're going to have a 188,000 Gauss magnetic field, and that is close to as big as can currently be made uniform. So now you have a magnet that is even bigger and needs to have its own room in order to house it, and flux lines that go very far out. And the limits on commercial instruments these days are about 900 megahertz, and the thing costs, I guess ours cost about, for the whole thing, about $2.5 million. And by the time you're at 900 megahertz, it's many, many millions of dollars. And there may be I think 1 gigahertz out there, but we really, for now at least, seem to, what?
It's in France or something.
I think so. We really seem to have just pushed the limits of technology for how much electricity you can put in a superconducting coil without it just ripping itself apart. All right. So the other quantity we have in this equation is gamma. Gamma is called the magnetogyric ratio. Sometimes you'll hear it referred to as the gyromagnetic ratio. This is a property of the individual nucleus. The bigger the gyromagnetic ratio, or bigger the magnetogyric ratio, effectively the bigger the nuclear spin, the bigger the magnet that the nucleus is. Protons actually are good. They have one of the biggest magnetogyric ratio of any nuclei studied, 26,750. Oops. And it's 53, what am I thinking here? And so just to put this into context, at 117,500 Gauss, in other words, the relatively large magnet, so at 117,500 Gauss, you have the nuclei flips its spin at 500 megahertz. If we look at C13, we get a gyromagnetic ratio of 6,728. And that corresponds to absorbing energy at a frequency of 125.74 megahertz on this 117,000 Gauss magnet. So one of the implications, remember I said you were dealing with very small energy differences. One of the implications is the energy differences are even smaller for carbon than for proton. So now you're getting doubly damned for carbon because the natural abundance of C13 is only 1.1%. So most of your carbons aren't even C13. Indeed, with small molecules, most of your molecules don't even contain one C13 in them. We saw that in mass spec, where you see the C13 isotopomer peak, And for the small molecules that we were looking at, that peak is small compared to the C12 isotopomer peak. But you're getting damned again because its small magnetogyric ratio leads to smaller energy absorption. Now, the other thing you have to remember is even though you're recording your C13 NMR spectrum on a, quote, 500 megahertz NMR spectrometer, you're not reporting your carbon NMR at 500 megahertz. If you were, you'd be that lucky person not in France, but maybe on Mars, who has access to a 2 gigahertz NMR spectrometer. And there ain't no such animal right now. All right. Fluorine-19 isn't so bad. Its magnetogyric ratio is 25,179. So that corresponds on the same spectrometer to 470.58 megahertz. Usually it takes certain types of probe technology, we'll talk more about that later, but certain types of coil technology to tune to higher frequencies and certain type of coil technology to tune to lower frequencies. So often if you want a really good proton NMR, you will use a special probe where the coil that's tuned for proton is inner and close to the sample, and the coil that's tuned for other nuclei is bigger and further away from the sample. That sort of probe won't be as good for carbon-13 because you have the coils further away from the sample, the coil that's good for C13. Conversely, if you find that Phil Dennison has put a broadband probe in the spectrometer where the nucleus at the lower frequency is inside in the coil, you may find that the proton NMR it collects is not as good or is not as sensitive or is not as sharp and well shimmed because the coil is further out. Fluorine is interesting because often you can use the same coil for both fluorine and for carbon, and for proton. Phosphorus also has a smaller magnetogyric ratio. It's 10,840. Now remember, fluorine and phosphorus have all of their naturally occurring nuclei as F19 and all of their naturally occurring nuclei as P31. So these are not damned by the low isotopic abundance the way phosphorus is. Another nucleus that's sometimes studied is deuterium. Deuterium, we talked about the nuclear quadrupole. You also have your lock coil in there. The magnetogyric ratio for deuterium is 4,107. So that means your lock frequency on this spectrometer is at 70,076, is at 76.76 megahertz. Well, the cryoprobe technology is really wonderful. What they've done in the cryoprobe technology is they have cooled the probe, and it's either I guess it's not a superconducting probe, but what it is a very low noise probe. And because the electronics of the probe are cooled, so you don't get much electronic noise. And the result is it's very high sensitivity. And we were fortunate. They had just, when we bought it, they had just developed technology that had both carbon and proton sensitivity. And basically, it was special coil technology. So that instrument is super good for proton. It's got a huge, just an incredible signal-to-noise ratio, better than even the 800 megahertz spectrometer. It's also super good for carbon. I want to come back to these magnetogyric ratios because you've seen this with your own eyes. Now, we already talked about the coupling, the J1CD coupling in chloroform. And remember I said you see this 1-to-1-to-1 triplet in the C13 NMR, and the separation of the lines is 32 Hertz. Well, if you've ever looked hard at your chloroform peak in the proton NMR, so here we have our DC coupling, our H2 coupling. But if you've ever looked hard at the chloroform peak in the proton NMR, what you see is something like this. You see a main peak for your CH, and of course what you're looking at is chloroform. But you also see two peaks here that are the C13 satellites. And those correspond, so this is your C12 peak, and those correspond to the J coupling to the C13. In other words, what you're seeing here is a doublet, and the separation of those two lines is 209 Hertz. And the mathematical relationship between 209 and 32 is the same as the mathematical relationship, the ratio between 26,753 and 4107. In other words, it's 6.5. In other words, the magnetogyric ratio is 6.5 times bigger for a proton than for a deuteron, and we see that directly in the J coupling. The effect of the magnet that the deuterium has in splitting the carbon is 1/6.5 the effect that the carbon has in splitting a proton, because coupling is mutual. All right, the last thing I want to talk about, I've talked about how damned we are by energy being low. I've talked in the case of carbon about isotopic abundance. But now the really damning thing ends up being the Boltzmann distribution. That is the population of the spin states. In the case of a benzene, all of your molecules are in the ground electronic state. In the case of a ketone, all of your carbonyls are in the ground vibrational state. But in the case of nuclei, the energy difference between the alpha and beta states is so small that both are populated. And if you think back to your P-Chem and you calculate the number in the beta state versus the alpha state, that's going to correspond to the difference in energy, delta E over KT, where K is their Boltzmann constant. And then if we just remember that delta E equals H nu is equal to H times gamma times B naught over 2 pi. And then we say, OK, let's just take at 70,500 Gauss. That's our 300 megahertz. And let's plug in N beta divided by N alpha is equal to, and if I plug in, that's e to the negative 6.63 times 10 to the negative 34. Times the magnetogyric ratio, 26753, times 70,500, the applied magnetic field, over 2 pi, divided by our Planck's constant of 1.38 times 10 to the negative 23. And let's say we're saying at 298 Kelvin, so I say 298 here. And when I work that all out, what I get is this number comes out to a quotient that's very, very, very close to 1, 0.99952. 4 nines and 5 2 corresponds to the ratio in the beta state over the ratio in the alpha state. In other words, we have 48 more protons out of 2 million So where all of your carbonyls are available to absorb a photon, because remember, when you apply a photon, it can either kick a nucleus up from the ground state to the from the alpha state to the beta state, or down from the beta state to the alpha state. So it's only that differential population, only that 48 out of 2 million that are available to absorb. If we apply a higher magnetic field, it only gets linearly or almost linearly better. At 117,500 Gauss, remember that's our 500 megahertz, then we only get to an N beta over an N alpha, in other words, a relative population of 0.99919. In other words, it only gets a little bit better. It's only 81 protons out of 2 million. So we are damned by the low energies. We are damned by the low differences in population. And this is why NMR, compared to other spectroscopic techniques, is very insensitive and why it took a long time to develop. Next time, we'll talk about how the NMR spectrometer works, how we absorb our energies, and then how we translate that into a spectrum. And I'll also talk a little bit maybe about some of the aspects of the spectrum.